Hi everyone, it's Mrs. Bustamante. We're continuing our discussion about osmosis and water movement. So here's an isotonic solution. What's the definition of an isotonic solution that we kind of briefly talked about? That's where we have no net movement of water across a plasma membrane. Notice it says net movement. That means we do have movement in both directions. It's just equal in both directions, right? So this means that the volume of your cell is stable and water moves across the membrane at the same rate in both directions. Here we can see like an animal cell, for instance, we see water moving in and we see water moving out. And here's a plant cell, we can see water moving in and water moving out, and it's at the same rate. So we say there's no net movement. A hypertonic solution is where the net movement of water will be out of the cell. So that means water is going to move out of your cell because your cell is hypotonic compared to its solution, and we know that water will flow from the hypo, right? Okay, so in an animal cell, oftentimes this will cause the cell to shrivel or crenate, kind of like crinkle up, if you will. And then some plant cells, right, this is called plasmolyzed. That's where the plant cell too kind of shrinks up. Not as much because it has a cell wall. It's important, but that's where your plant would look kind of limp and like it needed to add some water to fill up that big huge vacuole in the middle of it, right? And then a hypotonic solution, how would water move if that cell is put into a hypotonic solution? Well, if you have an animal cell and you put it into a hypotonic solution, right, water is going to move into the cell, and sometimes if too much water moves in, that will cause the cell to burst or lyse, we say. Some cells actually have specialized organelles that will help pump water out in order to avoid this. And a plant cell, we say that this is where the cell is turgid, which is actually kind of good or normal, right? That's where that cell is kind of plump and your plant would look nice and bright, right? That it's filled with water. That's kind of how we would like it to be. And in this instance, our cell wall kind of helps keep that plant cell from bursting like we see in an animal cell, right? Kind of adds some structure and helps it maintain that structure and not burst. Okay, here's a nice little chart. So this is your solution surrounding the cell. If it's hypotonic, that means your solute is lower, your solvent is higher, and net water movement will be into the cell, causing the cell to become larger. Cytolysis is where animal cells will burst as water enters if they get too much water in them. And then turgor pressure is in plant cells where the plant cell wall pushes back against the water pressure entering, preventing it from bursting. So the cell wall kind of protects it. Hypertonic solution, outside is higher solute, lower solvent. Water is going to move out of the cell and it will become smaller. Crenation typically is in red blood cells, animal red blood cells. When we talk about it, it's going to shrink. We're going to see a picture of it here in a second. And plasmolysis is where plant cell membrane pulls away from the wall because the vacuole is becoming smaller and smaller. And then isotonic, well, I just put move back and forth or kind of the side arrow, right? Because it's equal to the solution inside the cell, so it remains the same. Just as kind of interesting note, when we talk about red blood cells here in a second, red blood cells actually require a 0.9 salt solution to be surrounding outside of them in order for it to be an isotonic solution, which is important, say, when you're getting an IV of something, right? You actually want to have the right concentration that's entering into your bloodstream. Okay, so here's a picture of these. We have animal cells over here. These are actually red blood cells, right? What happens to red blood cells? If you put them in a hypertonic solution, well, that water net movement is going to be out. Now remember, water still moves in and out, but the net movement will be out of the cell, causing it to shrivel. Isotonic, you can see in and out, equal rates, nice and plump. Hypertonic is where more water moves in than moves out, and so they might burst or lyse. In plant cells, right, this looks a little bit different. Plant cells, hypertonic, again, kind of shrivels up, but it's more so that it pulls away from the cell wall because that cell wall is protecting that shape. Isotonic remains the same, and hypertonic is turgid, how we actually want it, nice and plump, pushed up against that cell wall because water has moved in and it keeps it nice and stable. So this is where I also like to bring up like slugs, right? Because some people don't do this. It's not nice to the slugs, right? We'll put salt on the outside of slugs, and if you do that, you will notice that the slug will kind of like shrivel up and eventually die, right? Why is that? Well, that's because you changed the solution surrounding the slug, right? And you're causing all the water inside the slug to move out of the slug in order to equalize that salt concentration on the outside of them. And so they don't make it. Don't do this. It's not nice. Be nice to the slugs. Okay, I hope that was helpful and have a great day.